Hi everyone, I'm Yu Chen Lin. You can also call me Jason. Today I'm talking about my dissertation proposal, Information Recovery in Online Social Networks, Identification and Localization. For the online social networks, like for example, Facebook, Twitter, Quora, there are two main problems. One is missing attributes are a common problem we will see. So the first observation is how do we label these missing attributes to make the data quantity more complete and more big for in a big data. Second problem is observation is that even with the same labeling, um, each item may have different degree of tendency. So how do we differentiate these items with distinct properties? This would help improve the data quality. Among these Facebook social data, our interest is in the Facebook public pages. For the Facebook public page, as we see like this is a Golden State Warriors Facebook public page. And these public pages are usually the public profiles used by local business, companies, organization, or public figures, for example, politicians, musicians, etc. So pages hosts can decide which pages they like. So, for example, this Golden State Warriors page they like other pages like Sports Illustrated. Yeah. Like for this formulates a public page graph. In this graph, if we take Golden State Warriors as an example, um, Golden State Warrior like Sports Illustrated, Oakland Museum, and also Given Tuesday. For each page, they have information like page ID, name, category, country, fan count, and description. So, in my proposal, there are 30 research questions. Among these various attribute information, location attributes are of particular interest to social scientists since these digital footprints give social scientists insight into users' physical footprints outside of the OSN, online social network. So I try to explore and approach these research questions. First, how do we identify missing nationality information of pages? Second, what kind of challenges will we face when the identification becomes fine-grained? How can we, for example, how can we identify the subdivision like U.S. states labeling of pages? Third, how do we differentiate local pages from global pages? So these are the 30 research questions I like to approach in my dissertation proposal. There are some related work. For first, Facebook user graph profiling. Uganda in 2011, they analyze the Facebook user friendship graph. They characterize its global structure and related network properties. Second direction is a Facebook user analysis. Dr. Barney examined international relations among countries by building connections from co-occurrence of country keywords in Facebook's users' posts. One used the linguistic keywords and word counts to show each public page has its own characteristics. Also, framing phenomenon exists in political and news pages. However, This previous work do not leverage the relationship among public pages to analyze cross-page user behaviors. Third direction is the user geographic location prediction, geolocation prediction. The big part is use content-based keywords analysis. They take advantage of text messages related to a strong local geoscope. Yeah, many papers talk about this. Second part is using social ties, like friendship relationships among users. And third part, get better results. They use cluster analysis in various region granularities. In 2014 and 2017, actually they use geometric mean, k-means clustering, DB-scan, and also Gaussian mixture models. Yeah, so the mainstream is using this location keyword from a text to infer Twitter users' location. So in the following, after introduction, I will first talk about the identification of pages nationality. Then I will talk about how we profile Facebook public page graph. Then talk about the sub-region identification of pages. Then global page detection, and the last is my future work. So why are nationality information missing? Because page hosts can choose not to uncover geographic location of pages. In our data, 8 million, around 49.76% out of 60 million pages show country information. Thus, we based on this data, we propose an efficient algorithm to identify country information. Our spirit of design this algorithm is that since the majority of public pages are commercial in nature, they tend to use more accurate location data. As users have no such intrinsic motivation to provide accurate location. This means the quality of location attribute data is much higher of pages than for users. Thus, we can directly use these data as golden for our training and test and verification. For the data collection part, we use Facebook Graph API version 2.8 to collect our data. We use a strategy of snowball sampling. It starts from a set of popular public page as seeds. Then the crawling list expands by adding into this list pages which are liked by listed pages. For example, so our list would keep growing and growing after each iteration. So for our majority vote algorithm, as we can see in this algorithm, the purpose is identifying nationality of public pages. The vertices are pages, edges are like, so like connections, and we take it as undirected here. The observation is most neighbors come from same countries. So the concept is we use majority vote by neighbor's nationality. So for each time we use majority vote and it's sorted by the items known neighbors. The more neighbors known, the first they would be predicted. So each time we vote, and based on which candidate have most votes, so we take it as the predicted result. So the time complexity is E plus V log V, and the space is E plus V. The performance evaluation. For the accuracy part, we got 90% accuracy with 50% unknown country pages as a data we got. So we took this percentage for our training and testing. The F1 score is 0.904, which is computed by Precision and Recall. Our processing order is by number of known country neighbors. The accuracy, as we can see from this figure, this accuracy remains over 90% while a page has at least 30 known neighbors. For the robustness part, we test this by changing the unknown country pages ratio among all pages. So the accuracy is over 90% when unknown ratio is less than 60%. The standard deviation is more than 0.15%. Okay, so the next part we will talk about profiling of Facebook public page graph. This part, we will first talk about page distribution, then connectivity, and last we will talk about country international impact. And these have 3 subparts: social influence and correlation clustering. So we would profile from these 3 aspects to analyze countries' international impact. For the page distribution by country, we can see among these 60 million pages, 41% are US pages, and the second highest is UK. It got 5.5%. So this in top 10 count 70, we can see the imbalance. Like top 10 countries occupy nearly 70% of pages. This reflects Pareto principles. For the page distribution, if we see from by category, we can see that there are actually in Facebook there are 1,459 categories in total. But here it would be too hard to analyze if we take all these 1,400 categories into analysis. So actually, we found that only top 100 cover 91.5%. Again, this Pareto principle. So we classify top 100 pages into these top 100 categories into 7 broader categories. So we classify these top 100 into 7 broader categories. As we can see from the figure, that the sum of company and organization and local business, it accounts for over 60% of all pages. And in a lower figure, we sorted these pages by categories, and also by we sorted these categories by these pages by their number of companies. So we found that a company and organization and local business and places are major parts in most countries, and they almost occupies similar percentage. So we can find that actually in Facebook, these public pages are commercial promotion, commercial oriented. So for the connectivity, our results found that average degree is 62, median is 17, and 77.5% are domestic ages, means these ages do not go out of that country. Most connections are pages within the same country. And we run breadth search from the highest degree page in each country. Nearly all countries are closely connected, within 5% in BFS. For the international graph, we define it as V and E. The vertex is the international vertex and also age. These international vertex are aggregated by all public pages whose nationality are the same country. And the international age are a set of directed ages, denoting that the source nations like destination nations, and they are belonging to the different countries. So for PageRank, PageRank analyze the relative importance of a vertex in a graph by calculating probability that a vertex will be reached when starting from a random vertex. The algorithm assigns an initial probability value to each vertex and then iterative updates probability value of each vertex. So we can see that this for V1 to Vn, the vertex represent all countries. The BVI is a set of vertex which like VI, the vertex of this country. And also the LVI is the number of likes from vertex VJ, which like VI. And so the probability D is a damping vector for continual traversal, and N is a total number of vertices. So each iteration will make the probability of PageRank more to the make it more to the final result. So it's an iteration. Botunian centrality finds information hub in the network graph. It measures number of shortest paths which pass their vertex. Higher Botunian centrality means that more information will pass their lab vertex by connection of ages. The vertex with high Botunian have higher potential to disconnect graph if removed because it's a more important hub. So we use PageRank and Botunian centrality to measure the important social influence of a country in the international impact. We can see that the Botunian centrality and also PageRank, not surprisingly, that the US and UK got very high Botunian centrality and also the PageRank. Another surprising result is, for example, another need to notice result is the New Zealand and Switzerland. Their number of pages much lesser than the other countries. For example, New Zealand only has 86,000 pages and Switzerland only has 53. But actually, when we rank by PageRank, they are in the top 10. So this table is the top 10 PageRank and also top ranked by PageRank for the top 10 and also Botunian centrality. And they have 8 countries overlap, which is a very high potential, high ratio of overlapping. So so the underestimation is that there are several factors we didn't consider in Facebook data. Um, the mainly results from the low involvement in Facebook. For example, China authority forbids Facebook, and most China people they use Weixin, WeChat, or QQ instead. Um, Russian people use Vikonte, VK, that is much more popular than Facebook in Russia. For the country international impact, we try to analyze from the correlation aspect. Um, we use Kendall's rank correlation coefficient. This ranking list of attributes are compared in order to examine the correlation among attributes of vertex in the international graph. Kendall's rank correlation coefficient this talk is calculated by the NC and ND. NC is the um, NC is the concordant pairs. ND is the discordant pairs, means the orders are the same, means concordant pairs. And discordant is not the same, means xi greater than yi, then xj greater than yj, then it's the concordant pairs. So this Kendall's rank correlation efficient is 1 if two ranking lists are the same, -1 if it's totally reversed, 0 if they are independent. So we use this correlation to analyze number of pages, page rank between its centrality, and also number of page nations connected. And we found that the countries connected to more nations. The most is the page rank and number of nations connected. This means the countries connected to more nations have higher impact. And also, the increasing number of nations connected connects in higher social influence in between its centrality. However, the number of pages does not necessarily guarantee more important information hub from the correlation of number of pages and also betweenness. The last part we talk about the clustering from a clustering aspect. Clustering is applied to find community structure. The modularity function Newman proposed as modularity Q equals fraction of within community ages minus expected value of this fraction if ages were distributed at random. So this ki kj over 2 times m is the expected number of ages between I and j if the ages are distributed at random. So the delta Cij is 1 if Ci equals Cj, the community are the same, and 0 otherwise. The Aij is the actual number of ages between I and j. So actually, this modularity talk about how an item is tells us if an item is belong to a community. So for clustering in the application, we apply two-phase unsupervised fast algorithm to calculate the modularity. This proposed by Blondel in 2008. This two-phase algorithm has some advantage because it's unsupervised first, so we don't need to designate a class number first, and it's much faster because this clustering problem is an NP-hard problem. From the results, we can see that there are two groups the reds and the greens primary. Also, there are blues, but the two primary are the green and the red. The reds consisting of Western nations like United States, UK, and greens consisting of Islamic countries. They use Arabic language at most nations. This phenomenon very interestingly supports Huntington's argument. Though technology makes world a smaller place, difference among civilization due to language, culture, and religion are too basic, so that they cannot be gone soon. The next part we will talk about the subregion identification of pages. There are 6 parts in this subregion identifications. First, we talk about motivation and problem statement. Next, we will talk about the challenges in this subregion identification, and talk about the algorithm we propose for the baseline and advanced algorithm. And then we'll talk about our data set and our experimental results. The motivation is that the fine-grained attribute identification facilitates information precision, so that we can make the public pages information more fine-grained and more accurate. This is very useful, especially for marketing, advertising, and also regional social research, because in these applications, the more accurate we can identify a page and lane users, so that our communications will get more impacts. So what are the challenges when dealing with finer grained attribute identification? The problem statement is, for example, how can we actually identify state labeling of pages in the United States? First, our first thought is, can we just apply majority vote algorithm? So location, here we generalize this majority vote algorithm, so that location designate a state information in this scenario. The location labeling is determined by the most votes, and however, this overall accuracy is just only 59%. Randomly select 50% as already known pages as unknown pages to make the distribution as the page distribution. This algorithm works well in a page nationality prediction task with 90% accuracy. However, it does not work very well in this subdivision identification. So we think about what are the challenges. Different countries may speak distinct languages, but states do not. Most people they speak English. So one public page is less likely to follow another public page, which use a different language. So this property cannot be applied in the state identification. Second, the communication among countries is much less than communication among subdivision regions, which are domestic. These communications and it is very is more complex. So relationally, states in the U.S. are much closer to each other compared to countries. For example, different states may share the same culture, language, and proximity. So this all contributes to the low accuracy when the majority vote algorithm is applied. Then we talk about our baseline algorithm to deal with this. First, we consider utilizing the locality of states to find pages belonging to their corresponding states. So we pick out anchor pages. with local property as multiple seeds to start breadth-first search from. Our target classifier has 51 classes. So 50 classes of United States and a class of others, OT. So we propose a state distance vector, which is composed of two parts, I hub and O hub, from the page to a specific anchor state page. So yeah, so the I hub is the hub distance between the page and the seed SI for the inward and outward. For the anchor page selection, the effectiveness of breadth-first search algorithm depends on the algorithm depends on anchor page selection. So the anchor pages have to be as local as possible, such that the SDV can provide authentic tendency of pages locality. Suitable examples focusing on how do we choose these anchor pages. Our strategy is focus to find those pages that focus on local communities, like for example state universities, government, park, police organizations. EO-suited examples like those popular and thus have global impact. For example, NBA, MLB, NFL sports team. So, in general, we adopt here in our experiment, we adopt all subsidiary pages of onlyinyourstate.com as a set of anchor pages. This website have a distinct page for each state. Each subsidiary page most connects to the local communities. In particular, because California is much larger than the other states in a perspective of population and economy. Onlyinyourstate.com splits California into northern California and also southern California, as we can see in the table. Therefore, we took both the only in North California and also only in South California, and for our anchor pages. Furthermore, only in Idaho has been registered, so they named its Idaho counterpart as Idaho only instead. For our advanced algorithm, the baseline drawback is that a local page can have a few connections with those pages far beyond the state where it resides. The reason is that they may have several middle or they just have like connection with the anchor page, so the hop distance is small. So this kind of connection noise would highly reduce the prediction accuracy. Therefore, we define another feature vector that is state neighborhood probability. This state neighborhood probability has two parts: INP for page and the region RI, and also an OMP. The region RI is a state. So INP denotes the inward neighborhood location probability between this page and the adjacent pages belonging to a region RI. So the IE is the number of inward pages between this page and the adjacent pages belong to the region. And also, we divide it by all the inward edges number. So then we got the state neighborhood probability. So both this SDV, state distance vector, and SMP are taken as feature vectors for our machine learning models. So we utilize both locality and neighborhood context for better location identification results. For our data set, we use 50 million, that is 38.93% out of 38 million pages, which have distinct information as our golden. 2 million are US pages and 12 million are non-US pages. California accounts for 20% of all US pages and half of all pages, around 50%, are located in top 5 states: California, New York, Florida, Illinois, and Texas. So we map city to corresponding state in which it resides. This is our accuracy summary. We use several classifiers for the baseline for naive Bayesian, AdaBoost, random forest, and also random forest for the advanced breadth search. We can see that we use training set utilize 80% data, the test use 20%. Because the number of classes is really large, the random forest classifier is preferably adopted. And we can see that in a baseline, the random forest got 69% precision. Also recall, and F1 score got 68%, which is much higher than the other two classifier. So in the following advanced algorithm, we only use random forest algorithm. And also we can see that our algorithm is in a baseline is 10% better than the majority vote algorithm. In the advanced algorithm, we have precision 89% and also recall 88% and F1 score, which is almost 90%. This is a detailed accuracy of by state. So the results of at least 20% better are marked in blue colors. We can see that mostly advanced algorithms, precision, and recalls are 20% better than the baseline counterparts. And here we can see the bold part is the worst results among all states. The class of New York got worse prediction result in the baseline and also the advanced at 48%. And California only achieved 50-30% accuracy in the baseline. These two states accounts for the most public pages. A page has higher probability connecting with pages in these two states, so which results in the lower accuracy. So yeah. So the Nevada got worse results in the recall and F1 score. Yeah, also because it's more commercial oriented. For the advanced algorithm, it beats its counterpart in all states. This tells us that the combination of SDV and SMP works. The results of advanced algorithm are at least 20% than most baseline counterparts in half states. And most states have F1 scores greater than 0.8. Also, we check our results from the confusion matrix perspective. For the baseline, we can see the green part is the correctly identified results. The pink part is the first most misidentified class, and the orange part is the second most misidentified class. The third misidentified class is the yellow one. So main color grids come from these in the baseline come from these 30 states: California, New York, and Florida. These top 30 states account for most pages on Facebook, and consequently they have a higher tendency to connect with other pages. OT is other countries, other regions. Other countries, this is another primary source of color grids. So with only half distance considered, a page is more likely to have multiple minimal hop without leaning toward a specific state class. Thus, in this case, they are easier to be classified as other countries, because the classifier cannot judge which state they should belong to. Geographically, neighboring states could skew identification result. For example, like CT and MA. Like Connecticut and Massachusetts. For the advanced algorithm, we can see it's much more regular because most color grids come from the top 5 page populous states like California, New York, Florida, Illinois, and Texas. This is a side effect of incorporating neighboring page probability, since these states have more edge connections than the others. Far fewer color grids, also lower percentage values in OT, because our advanced classifier is more effective than baseline. The strong ties outside top 5 page populous states are Delaware and Pennsylvania, and NHNMA, WV and NC, and also WY and Colorado. This suggests that these state pairs have strong ties. The next part, I'll talk about our global page detection. Motivation is localization, because locality differentiation facilitates the subtle division of information for different audience. Also, regional analysis, they want to remove the pages which are global. So regional analysis in social research also needs this kind of methods. The other one is understanding location of target audience in marketing strategy. For example, BMW has distinct advertisement based on elements such as geography, culture, and language. For the media, CBS broadcasts different messages to different groups by dividing its viewing audience into separate groups based on geographic data. So observation is that pages which have connection with multiple regions and do not lean toward a specific region, we define this as a global page. So there are two kinds. One is international, one is interstate. So from observation is that given all pages located in US, some have characteristics that are similar to pages in other countries, or they do not belong to any state. So we we define it as globe page as P. P belong to a page set, and also they have a delta J. J belong to the class set, and it's greater than the number of global threshold. So delta J is 1 if the delta Pj is smaller than the minimum of delta Pk plus within an error. So the delta Pk is the distance sigma omega I times dpi, the distance between the page and the class I. So delta J is 0 otherwise. So we define global pages as those pages which could be classified as multiple region classes within a small error distance. Our detection flow is for a page. We first within the U.S. we first check if it's within U.S. or not. If not, then we label it as OT, other countries, or other regions, and then we put those pages within U.S. We put it into a classifier, and this classifier will label it as either local state or label as OT. If it was labeled as OT, then it's a global page. So global pages are within US but have characteristics international, similar to pages in other countries. Interstate means do not link toward a specific state. So for our experiment setup, minimum hop distance of a page, M hop, is the minimum of also I hop, inner hop distance minimum, and also the minimum of O hop. So the M hop is a minimum of both directions of hop distance. So local pages in US, they have local tendency, are the pages with number of M hop smaller than number of local threshold. Others, global tendency with pages with number of M hop greater than number of global threshold. These are several global page examples in our experiments. The left part is the international page located in New York. It's more like Middle East contents. And the right part is the interstate page located in Louisiana. So for this is more like commercial oriented. It's a Tabasco. Yeah. We see a global page. We also we take a look at the global page distribution by state. It's 1% on average. However, New York, not surprisingly, New York has the highest global page ratio. It's around 4.72%. This result is consistent with our image that NY is a global melting pot. California is the other state whose global page ratio is higher than 2%, which shows its global diversity. Also, we want to take a look from the demographics point of view. So we rank states by the ratio of number of global pages over population density. As we can see that Alaska in this rank, Alaska ranks first, which manifests its endeavor in travel promotion. And the following are the most populous states like California, New York, and Texas. The last part is my future work. First, I like to do the user location attribute prediction. Motivation is that although many people are doing this, people already done this kind of location attribute prediction. They are mostly text-based and it's easily fooled by malicious users and less vulnerable. So I like to build this user location attribute prediction model by features which are hard to fake, like users' activities on public pages, and also users' activity time, users' language habits, for example. The challenges are first it's multiple languages and similar behavior in the they may have similar behavior for the same ethnic group. So the second part, I would work on the analysis of global pages and also versus local pages. The motivation is this localization is an intrinsic property, which may affect pages' characteristics. So my expectation is I want to explore the community difference between global pages and also local pages, and how this distinction affects various users' characteristics like number of comments and reactions, frequency of comments, and also nationalities, something like that. The last part I like to work on adversarial page. Last direction is I like to work on is the adversarial page injection analysis. Like we can see in the right figure, Heart of Texas is the most popular Texas secession page on Facebook. This was revealed to be a Russian front. So the common deficiency of machine learning algorithms reside in the robustness when facing malicious attacks. So the challenges are how do we detect the data manipulation in different strategies? Because each different strategy may have different features and different characteristics. And the other is how do we the hard part challenge is to collect data for evaluation. So my research schedule for these three future work, user location prediction is just started, so may take 3 to 6 months. Analysis is around 50%, so may take another 3 months. The adversarial page analysis is not yet started, so may take half a year to one. So I have until now I have 3 publications. 2 are working with Dr. Bonnet. So I like to thank him for the great advice. Thank you. Any question?